Welcome once again to the course Metallocene and Metal-carbene based organometallic compounds as industrially important advanced polyolefin catalysts. If you recall, in the last two classes we discussed and tried to give a flavor of the socio-economic impact of the polymers in our life, and we discussed the demand of the polymers, mainly polyolefins, different type of polyolefins we tried to classify, and we tried to understand the basic structure of the polymer. So, and also we tried to understand what is the basic difference between the polymeric compounds and the small molecules compounds. As you recall that we tried to discuss about the crystallinity of the polymers associated with polyethylene mainly because this will be important to in our further classes, where we will see that we can control the crystallinity by using the different polymerization protocols. Okay, so in this class, continuation with our last classes, in this class, that is lecture 3, we will discuss in more depth about the polyethylene and polypropylene polymers, and we will try to understand the chemical structure and its properties. So, let us start. Okay. So, in this lecture we will try to cover the polyolefin, the global status and demand, although we have discussed in the last classes. I will just try to give some data so that you will understand how much demand of particularly for this polyolefin category. Then we will try to discuss the polyethylene and polypropylene, and then we will discuss the structure property relationship, because this is very important, because suppose if I need a particular applications, I need to understand the structure which actually can give the specific properties for a particular application. So, structure, then property, and then applications. So, this one are interrelated, and again the structure again depends on the definitely on the monomers, and also you will see that in the last class we saw that same monomers can give the same polymers of the same composition, but with different architectures or different structures. So, the monomers and the polymerization protocol. So, we need to select a specific suitable monomer, suitable polymerization protocol to get our desired properties with the desired structure for a specific applications which we are targeting for. So, here the key points we will try to cover, and we will try to understand the polyethylene propylene chemical structure, and we will try to understand the tacticity. We will discuss in more detail in this class what is the tacticity and how these are related with the properties, and definitely for the applications. Okay. So, now let us, before going to the specific structural structure property relationship, let us understand why this polyolefin is in high demand and what is the advantageous properties. Although we have discussed in the last classes in a very brief way, first thing that you see that this kind of polyolefins are quite stable, thermodynamically stable, chemically stable, quite robust, and this robustness is basically due to the non-polar bond skeletal. As examples, carbon carbon, carbon hydrogen, those are very stable. As example, you see that polyethylene is this one. So, you have here like that. So, the polyethylene is basically the chemical structure the composition of polyolefin is this one. So, this is the polyolefin. Okay. So, here you will see that this R can be many things, maybe hydrogen, maybe methyl, maybe any halides like that, okay, maybe propyl, anything like that. So, these are the polyolefin category, and you will see here that two type of bonds, one is the carbon carbon, that is the this one, and here CH, that is the this one. Okay. Both the bonds are non-polar and very stable. You cannot really do any reaction in easy way. Okay. Although you can do in a very special way, that is the CH bond activation or carbon carbon bond activation, but you need a you need extra effort. So, here what is the I wanted to tell that these are very stable skeleton which cannot be broken in easy way. So, that is why it is very stable, and that is actually prompted to use in our daily life, okay, applications. So, this one was actually first reported in 1933, quite long ago, okay, and these associated properties, as I told, the chemical stability, okay, high dielectric strength, high electric resistivity. That is why it is used as a insulating materials. You will see that in electrical appliances. So, the application is huge. Okay, you will see that many domains, various domains this is used, and one of the main reason is that apart from the stability is cost is very low and easy synthesizable. You can make it very easily without any complications, and this you can see that this pie chart you can get a from this pie chart you can get a feel that in which domains this kind of polyolefins, mainly the polyethylenes, are used. You will see that one of the major use is in the packaging industry. You will see that this one, the packaging industry. Okay. Then you will see this construction domain. Then you will see that in various applications in industry of electrical, mainly it is used as a insulating materials, transportation, okay, textiles, okay, and as I told, that packaging is one of the major domain of using the polyethylene, okay, or allied polymers. So, it's the demand is huge, and if you see from this report, that is the very recently published Materials and Technologies 2020, that you will see that if this is the population, if like that, this is a very roughly I am drawing. Okay. So, like that, okay, and the if this is the population and this is the demand of the polyethylene. So, this is my demand of polyolefin polymer, and this is the population. So, you can see that this is directly proportional, the demand of the polyolefin polymers is directly proportional to the populations. So, its demand is huge, and you can see that it is projected that in 2029 the market will be $142 billion. So, it is a huge. Okay. Fine. So, this is, I am sure now it is quite understandable, and now you can understand that how the demand it is. Now, let us go to the chemistry part, let us go to the polymer science. Before that, I just want to give overview that what are the polyolefins again, and what are the different type of polyolefins depending upon the structure. and depending on varying the substituents. As example, you will see here, this is polyethylene, this is we know. So, this is this one. Okay. Now, the polypropylene, as the name suggests that this is so there is one methyl, sorry, okay, sorry. So, this is so this is polypropylene, polybutadiene, polyvinyl chloride, simple. So, instead of methyl, this is chloride, and EPDM is basically a combination of the different monomers to tune its physical properties. I will show the structure later. As I told, the beauty of the polymers is that even though the same composition, but depending on the structure, the chemical structure, the properties varies a lot, and this can be advantageous to develop a different polymers of the same composition, but with different properties and for different applications obviously. As example, you see like for polyethylene, this is high density polyethylene. Normally this polyethylene is 4 types: HDP, one is the low density polyethylene, LDP, one is the linear low density polyethylene, and one is the ultra high molecular weight polyethylene. So, here as the name suggests, the high density polyethylene is basically looks like this one. That means there is no branch in the polymer skeleton of the polyethylene, and LDP is like that. So, there will be lot of branching, okay, lot of branching like that, and in LLDP is basically that you have a main chain and you have a small branching. So, you see the name LDP and LLDP. So, this is the low density, this is the linear low density. That means the reduced amount of the branching or the controlled amount of branching, and this is the property is quite different from this to this, from this to this one, and also synthetic protocols are also different. That is why it is very important to understand that what kind of polymers I need to use for a particular applications, and what kind of chemical structure or engineering I have to do, and for that what polymerization protocol I have to follow. And this one, the ultra high molecular weight. So, you can regard is like very high kind of things. Okay. So, let us discuss in more detail about the high density and low density polyethylene. Okay. So, as I told that this is one of the heavily used, okay, polymers, and the reason, the properties I already explained. These I have just pointed out for your reference. Excellent chemical resistance, excellent electrical insulating properties, ease of processing, toughness, and obviously the properties are tunable. At least the mechanical strength, stiffness, toughness are tunable by changing the chemical structure and the polymerization protocol. Okay, fine. So, let us discuss in more depth. So, I already in the last class explained the classification of the polymers depending on the properties, okay, the rubbery state, thermoplastic state, glassy state, all those things. So, here you will see that high density polyethylene, the chemical structure, the cartoon diagram is like that as I showed in the last slide. So, this is basically the branching on the in the high polyethylene is almost 0 or very less. That means, obviously as discussed in the last classes, that the crystallinity that is the more orderedness, the crystalline domains will be higher, and that is why this kind of polymers, that is the high density polyethylene, will be more stiff and will show the thermoplastic nature. The use is this kind of HDP are kind of more stiff, more hard, and used is household materials. And this one is generally prepared from the Ziegler-Natta catalyst, although I will discuss in the following classes about in more depth about the Ziegler-Natta catalyst, the polymerization and the unique properties of this kind of catalyst before coming to the Metallocene catalyst. So, Ziegler-Natta catalyst to make the high density polyethylene, you generally follow the Ziegler-Natta catalyst, and here you will see that is these are more crystalline nature. So, if you you will get a sharp TM, that is the melting point in if you do the experiment, that is the DSC, okay, differential scanning calorimetry. As discussed in the last classes, that crystallinity you can measure by in a common two common ways. One is the DSC and one is the wax or powder XRD, okay, PXRD or wax. So, in DSC you will get the DSC is like that. So, this is basically y axis is the heat flow and x axis is the temperature. So, you will get with temperature like that. So, this is the Tg, okay, and this is the melting temperature, okay. Here XO up and endo down, and if you cool it, then you will get like this one, like this one. So, that is basically the crystallization temperature. So, when you are increasing the temperature, you will get the melting temperature, and then when cool down, that is you will get the crystallization temperature. Although this polymer crystallinity is depends on the thermal history, okay, as I very briefly discussed in the last classes that the polymer properties is little different than the small molecules. So, what happens that if you suppose you are synthesizing the polymer, and if you, normally we isolate by precipitation. So, if you do the phase separation in very rapid, then the crystalline temperature can show the amorphous nature, and if you heat it, what is called we generally call annealing, just below the melting temperature and keep it for some time, and then you cool it, you can get the melting temperature if we perform the DSC experiment. So, you have to be careful for that one, okay. So, for HDP you will get the nice crystallization temperature in if you do the DSC, okay. So, the here you will see for TM you will get 120 degree to 130 degree centigrade for HDP, okay. Okay, for and where the Tg you will get the minus 120 degree centigrade, okay. Let us come to the LDP. What is the difference? So, as I told that for a LDP you will get you will have in the polyethylene you have a quite branching. So, these are the branching, the branching is quite long, relatively longer, and number of branching will be quite good in number. So, that what will happen that in this case, okay, if you discuss like that, okay, this is, so it remain like that one, okay. So, but if it is the branching is less, then you can get some crystalline domains, okay, that is the origin of the crystallinity, but in this case this kind of scenario is not possible, and you will get the low density polyethylene, okay. and here you will see that these polymers will be quite soft, because the Tg is around minus 40 degree centigrade, okay, and Tm melting point temperature, okay, you will in many cases it may not be visible, okay, but if the side chain is less, then you can get the melting point temperature at around minus 130 degree centigrade, something like that. Okay. But again I am telling that depends on the number of branching and the length of the branching. Okay. So, this is about the and obviously this low density polyethylene depends on the polymerization protocols. For this one you cannot make by the Ziegler-Natta catalyst. So, here you have to, we generally follow the free radical polymerations. Why? Reason is very obvious, that we, for free radical polymerization we do not have any control, okay, about the chain length and the branching. So, generally for free radical polymerization we get the LDP, okay, and for SDP we have to follow the different polymerization protocol. Okay. Fine. So, LLDP is little different, and it is more kind of a chemical structure is more fine in nature. Okay. Here you will see you will have a long polymer chain and you will have a shorter small chain, okay, like is not like this one, okay, this one. So, shorter, and this is quite small compared to your main skeletal chain, and obviously the synthesis protocol is different than the others. Here we normally what we do, we use the ethylene, that is the main monomer, okay, that is your main monomer, and we used another olefin, as example hexene, octene or butene sometime, and we do the copolymerization basically with any of this one. So, we sometimes we call this the alpha olefin copolymerization. So, this is actually, in this case what we do, we use only one monomer, that is the ethylene, but in this LLDP we use the ethylene and also another monomer hexene olefin or butene, okay. These are the alpha olefin. So, this depending upon the ratio, how much we are giving or feeding, the number of the small branch chains will be varied. So, this is, you would see, is a very well defined LDP, okay, low density, which is basically linear low density polyethylene. And this kind of polymerization protocol is quite recent. We use normally the Metallocene based catalyst, that is the which actually our prime focus to study in more depth what is the how these kind of catalysts have been evolved, what is the mechanism, what is the chemical structure, what is the structure property, and what is the development. Okay. So, mainly the Cummings actually developed this kind of Metallocene based catalyst, which we will discuss from the next week classes in more depth. So, the beauty is that, or the most advantageous property is that you are basically the maintaining the flexibility and strength in one polymer. Why I am telling? Because in this case here, you see this is quite stiff due to the crystalline nature, and this one is more flexible. Okay. But here you will see that this is basically I am putting these two properties in a single system, and that is why it is more flexible. The flexibility and strength are on the same materials, and that is why you will see that this kind of polymers are heavily used nowadays, mainly in packaging industry, where you need the flexible material as well as you need a quite strong material. As example, for food packaging, pouches, bag, cable insulator, where you need a flexibility and also at the same time need strength. So, applications is used. Okay. Among these three polymers, the LLDP use of the demand of the LLDP is quite high nowadays in different domains, as I showed in the last bar diagram pie chart. Okay. Fine. Now, the next polymer, very interesting. Okay, we will discuss in quite depth about the chemical structure, is the polypropylene. So, the name suggests that this is ethylene, and so this is the polypropylene. So, obviously, this is for this one monomer is ethylene and this one monomer is propylene. Okay. So, that is the difference. Okay. Now, very interesting that if you see that this one, okay, this one here, if you recall the requirement of the chirality in organic molecules for sp3 carbon center, as example, like let us say for this kind of system where this carbon is sp3. So, A, B, C, D, that is the 4 arms, that is the 4 substituents on the carbon should be different. Okay. I am not going to the symmetry operation, I am very qualitatively I am discussing. So, here now here you will see that I have methyl here, I have hydrogen here, and in this case the number of carbon atoms will be different, their number of carbon atoms in this case will be different. Now, if you recall the CIP, okay, the rule for assigning the absolute chirality, I am sure you know that what is the CIP in organic chemistry you have studied, and if you forget, no problem. Okay, this is basically to assign the stereochemical center on a chiral carbon. Okay. So, this is Carl Ingold, Ingold Prelog priorities rule. So, here according to that one you see that this one is methyl, this is hydrogen, and this one will be carbon of different length, and there all carbon will be different lengths. That means, this center will be stereogenic, stereocenter. So, that is why a different type of different configurations are possible for the polypropylene. Okay. So, one is the isotactic, where all the centers, that particular methyl group will be, this carbon will be of the same configuration according to the CIP R or S. So, everywhere may be R, and this may be alternate RS like that. Okay. Like this one, you will see here the methyl are arranged on a particular direction. So, this, let us say if it is R, then this is R, 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 okay, according to the CIP priority rules. Now, if it is R, then one scenario may come, this may be R, this is S, this is R, this is S, this is R, this is S. Okay. So, here methyl is off, okay, and here the adjacent one, the methyl is up, but in the adjacent carbon you will see that methyl is down. Okay. So, in this case, this is called isotactic polypropylene, and in this case syntactic propylene. That means, there is a alternate arrangement of the methyl groups. Now, another possibilities is that there is no order. In both cases there is a order R, and in this case RS means there is a some pattern, some order. But in this another situation, there is a possibility that here R, here S, R, S, R. So, there is no pattern at all, there is no order at all. Okay. So, this kind of polypropylene is called the atactic polypropylene. Both are polypropylene, but in here it is you see this is atactic, and here it is called syntactic, where the alternate arrangement of the methyl groups, and here you will see that isotactic, where the methyl groups are oriented in one side of the main chain. So, polypropylene, that is why it is very interesting that it can give three kind of polymers based on the orientation of the methyl groups in the polymer skeleton. And the most beauty is that this kind of in this kind of structural variation, you will get the different properties. As example, you will see that as these are ordered, so isotactic and syntactic are semi-crystalline in nature here and here. So, that means you can get the clear melting temperature if you do the differential scanning calorimetry DSC measurement. As example, so this is the Tm is around 160 degrees centigrade, and for syntactic the Tm is around 150 degrees centigrade. Okay. But for atactic, you will not get any crystalline temperature Tm. Okay. Is a amorphous material, this one, because there is no order in the polymer skeleton. So, this is very interesting, and now let us try to understand in more depth why this stereogenic center comes. Now, you have to understand that this is a prochiral molecule M and H, that is the propene. Okay. Now, if you recall that if the reactant, okay, or let us say the metal center, okay. So, two ways it can react. One is the, let us say it is reacting with metal center. Suppose I am doing, let us say, Ziegler-Natta catalyst polymerization. Now, it can react in two ways. Let us assume that this propene, the plane of the propene is the plane of my computer screen. Now, so this one, so this is the plane. So, my methyl, my metal center can react with this way or can react with this way. So, that means through the below of the plane and above the plane. That means it can attack the re phase or psi phase, both ways, and depending on the attack you will get two different. So, if let us draw this one, how it is happening. So, here you will see that this is my methyl, this is this one. So, this can, if it is down, and another possibility is like that. Okay. So, eventually you will get this one and this one a different configuration depending on the how this metal center is attacking, whether it is a from the below the plane or the above the plane, and depending on that this one you can get the different stereocenters. Although in later classes we will discuss the two main mechanism how you can control the stereocenter of the polymers, that is the chain end control mechanism, and one is the catalytic site mechanism. So, that chain end control, that is the CSC, and catalytic site mechanism, that we will discuss later in more depth. Now, let us try to understand this is a part of the polypropylene polymer, let us say is just a small part. So, this is the polymer chain, okay, representing the spring kind like the bond. Now, here you will see this is my methyl, this is my hydrogen. Now, here this hydrogen and this methyl you will see both are below, okay, both are below, and here this hydrogen and this methyl you see that is the below the plane. In this case both are below the plane. So, I am writing below, and here you will see the above and below, and in this case you see that this hydrogen and this methyl are here the below and above, and this hydrogen and this methyl here again you will see that this is above and below. So, you will see below above, above below, below below, above below. That means, these two hydrogens will experience different chemical shift in proton NMR spectroscopy, but in this case it will experience the same here in proton NMR. Why I am discussing that this microstructure, what is called tacticity, this you can detect by proton NMR spectra, high resolution proton NMR spectra like 400 megahertz or 500 megahertz is good enough to detect this kind of tacticity in the polymer backbone. So, here you will see that in case of here, so this is R, this is also R, and this R you will see this is if is S, this is R. Okay. So, in this scenario you will get the different chemical shift where you have a same configuration on the two carbons, adjacent carbon center, and in this case you will have a different configuration in the two adjacent carbon centers. So, here you will see the same chemical shift. Okay. Now, there is another one here. So, this one you will see, if you this methyl and this methyl below the plane. So, if I draw the plane, okay, diagonally like this one. So, this one and this one is basically the mirror image. So, that is why this is we sometimes call the meso M, and this is we call the racemic R. So, this is the M, this is the R, where the meso, where in this kind of scenario this CH2 we call meso M, and this CH2 we call the R. Okay. So, if you go in this convention, okay, then what will be here? So, this one the R. So, this one will be M, this one will be M, this one will be M, like that, and this one again, this one will be R, this one will be R, this one will be R. So, for syntactic this CH2 will be M, R, and for isotactic this will be M. Now, what about the atactic, can you guess? Okay. So, this is RS. Okay. So, this one, this is RS. Okay. So, can you guess what will be there? So, for this one, sure. So, this will be like you see from the isotactic. So, this will be M. So, what will be this one? This will be R. What will be this one? Again R, because different arrangement of the methyl. So, here this one again, okay, R, and here this one again R. So, this is also another convention to represent the tacticity in the polypropylene type polypropylene or similar type of polymers. So, I will continue the tacticity on the microstructure of the polymers where the monomer is prochiral in nature in the next class. Thank you very much.